All right, guys, Mr. Jenkins here, back with the next lesson in Chapter 6, which is called Applications of Linear Systems. Okay, so just to kind of recap what we've covered so far in Chapter 6, 6.1 to 6.3 was basically three different methods of solving systems of equations. 6.1, we learned how to solve by graphing, which is a good way to start because you get that visual representation of what a solution to a system is. It's that point of intersection, if there is one. Then we learned how to solve algebraically in the next two. In 6.2, substitution, and then in 6.3, elimination. Okay, so today we kind of tie it all together. These are all word problems. And actually, we're going to focus less on how to solve them and more on just the writing of the equations, and then we'll use Desmos from there.
Anybody in this period?
Well, this is I'm doing like a flipped classroom,
Oh.
so I give them like videos.
Okay.
So yeah, wave of the future, baby. All right, so anyways, we'll go ahead and get started with example 1. All right, so pay attention in this video to kind of how I would like you to show your work. All right, example 1A says a fashion designer makes and sells hats. The material for each hat costs $5.50. The hats sell for $12.50 each. The designer spends $1,400 on advertising. How many hats must the designer sell to break even? Okay, and notice these are called finding a break-even point. All right. All right, so what we want to do first always is define variables. And since you have a system with two equations, you're going to always have two variables. All right, so step 1 is going to be define your two variables. And we're always going to use x and y since we're going to be using Desmos. All right, so in this problem, we have two things that could change. All right, a number of hats we sell could change, and then the money we bring in would change along with that. Since money depends on how many hats we sell, then that makes x, which is my input variable, hats. And my output variable, which depends on my input variable, would be dollars. All right, so as in any business, you have things that bring in money, and then you also have your expenses, right? So that's going to be our two equations. So step 2, and I also would want you to show this, would be, this is kind of the key part, writing the system. All right, so let's go ahead and write one for expenses. All right, so you kind of just have to read through it. So material for each hat is $5.50. So it's 5. So the cost per hat is $5.50. So we'll say money, which is y, equals $5.50 per x for per hat. Also, we've spent $1,400 on advertising. That's a cost as well, but that's a one-time fee. So there's my equation for expense, and then you have one for income. All right, so it just says what's bringing us in money. The hats sell for $12.50 each, nothing else, right? So y, which is our income in this case, is equal to 12.5 times x number of hats. All right, so that's my system. Okay, you'll see on the notes that I do show how to solve these algebraically, and I solve them by substitution, where I just sub in this expression right there. But we're gonna, like I said, focus less on that and then use Desmos from there. So step 3 is just, use Desmos. And interpret. All right, so I'm going to go ahead and type in my equations. Let's see. All right, so now you can see on the screen I have both equations typed in, and I can really only see one of the two lines. That means that I need to zoom out. And I need to keep zooming until I see two lines. All right, so had to zoom way out there, which is fine, but now we can see that point of intersection is 200, comma 2500. All right, 200, comma 2500. So our point of intersection was 200, comma 2500. So we've used Desmos to find the point of intersection, but now we also have to interpret our answer. It says, how many hats must we sell to break even? So is the answer 200 or 2500? Okay. Well, X is the number of hats. Y is the amount of dollars, right? So this means at 200 hats sold, our income is 2,500 and our expense is 2,500. So that's where we draw even. So the answer to the question is 200 hats. So this is how we kind of finalize our answer. In other words, if you just leave your answer as an ordered pair, that does not cut it here. Okay. B is pretty similar. Okay, so I'm going to leave that one for you guys. You can always ask to see that in class, and it is worked out on the notes as well. Okay. Moving on to our next type of problem. And you'll have some like this on Math Excel. So it says identifying constraints and viable solutions, right? So viable solutions means, would mean that an answer that makes sense given the context of the problem. So 2A, the local zoo is filling 2 water tanks for the elephant exhibit. One water tank contains 50 gallons of water and is filled at a constant rate of 10 gallons per hour. The second water tank contains 29 gallons of water and is filled at a constant rate of 3 gallons per hour. When will the 2 tanks have the same amount of water? Explain. So really, this is kind of a break-even problem in itself. It's just going to have a weird answer, okay? So let's go ahead and follow the process. Step 1, we're going to define our variables. So what's X stand for and what's Y stand for? All right, so what 2 things are changing here? All right, I would say on this problem, we have time that can change, all right? And then we have the amount of water in the tank that can change, all right? So the amount of water in the tank depends on the time. So X stands for time. If time's ever involved, that's always going to be your input variable. So time specifically in hours. And then our output Y is the amount in the tank. Gallons. All right, we've done that. Now we're going to use those 2 variables in 2 different equations. All right, so in this problem, we have, 2 different tanks going on. So our equations would be for tank 1 and tank 2. We'll just call them T1 and T2. All right, so one water tank contains 50 gallons of water and is filled at a constant rate of 10 gallons per hour. All right, so what we could say then is that, I'll set this one up. All right, so anyways, the rate here is going to be my slope, and then the amount of water that's already in the tank is going to be my initial value, which is my y-intercept. So we're going to go y equals 10 times x plus 50. The wording on this problem is a little weird, but just to be clear, that's saying there are 50 gallons starting out, and we're filling at 10 gallons per hour, okay? So for the other one, our starting point is 29 gallons, and it's being filled at a rate of 3 gallons per hour. So you might, if you just have some number sense and think about that, know that they're never going to really break even, right? If we're filling this tank at a higher rate and it's already started at a higher amount, they're never, tank 2 is never going to catch tank 1, in other words. All right, but let's see how this looks algebraically on Desmos. All right, so now you can see both of my equations have been typed in, y equals 10x plus 50, and y equals 29x plus 3. But notice I'm still way zoomed out from the last problem, so I can't really tell what's going on or where they cross. So that means I need to zoom way in. So bear with me on that. And as we zoom in, it becomes a little more obvious, where they cross. All right, so now you can see both equations are typed in. Y equals 10x plus 50, y equals 3x plus 29. I've gone ahead and zoomed in a little bit, and we can see that they cross. They're at negative 3 comma 20. So that means at negative 3 hours, they would both have 20 gallons in them, right? But since we can't go backwards in time, this is not a viable solution, right? So you have to be able to interpret that. So we'll just say since you can't have negative time, there is no viable solution. I forget how it words that on Math Excel, but it's going to be something like that. All right, so B is pretty similar, and you can see it worked out on the notes as well. Finally, example 3, solving a wind or current problem. I like these. These are pretty neat. So we might look at both of these. All right, so 3A, a traveler flies from Charlotte, North Carolina to LA. At the same time, another traveler flies from LA to Charlotte. The airspeed of each is the same, all right? So first of all, what do we mean by airspeed? That's going to be the speed of the wind, I believe, okay? And then the ground speed is shown below. What is the airspeed and what is the wind speed, okay? All right, so here's how you want to set these up. First of all, defining your variables is a little bit easier on this one because it asks me directly what's the airspeed, what's the wind speed, all right? So we'll just let x be the airspeed Actually, you know what? Airspeed would depend on the wind speed, so let's flip that around. So let's let y be the airspeed, and x is going to be the wind speed. All right, so yeah. So just to be clear, what they're talking about when they say ground speed, that would be, I guess, the speed of the plane if there was no wind, okay, affecting the plane. So the ground speed, well, I'm not exactly sure. All right. So, anyways, so yeah. Let's go ahead and set this up. All right. So it's kind of hard to see my diagram here, but it says on the from LA to Charlotte trip, the ground speed is 550 miles per hour. And you can see there they're going with the wind, okay? So that's what you have to get from the diagram. And then the ground speed from Charlotte to LA is going to be slower because they're going against the wind. It's 495, okay? So here's how you would set this up then, okay? So let's call this plane 1, and then this one will be plane 2, okay? So the one that's going faster is plane 1. The one that's going slower is plane 2. All right. So for plane 1, you would set it up this way. You would go our airspeed plus the wind speed. So y plus x or x plus y, doesn't really matter, equals the ground speed. Okay. So I think I misspoke earlier. So your airspeed would be your speed of the plane with no wind affecting it. All right. So the ground speed would be your actual speed. All right. And then plane 2 would be your airspeed minus the wind, right? Because it's taking away from our speed, equals 495. All right, if we were going to solve this algebraically, it would be perfectly set up for elimination, all right? But, it may even be quicker that way, but I'm going to go ahead and continue to use Desmos since that's the way I'm showing these. I think that'll end up saving you guys some time. And again, just to be clear, the work I'm looking for here would be define your variables, write your system, and then interpret what you see on Desmos, okay? So we have y plus x equals 550. That's one equation. And then y minus x equals 495. All right, and then we're going to see what we can see on Desmos. All right, so as it is, we really see nothing. So let me zoom out until I can kind of see both lines and look for that point of intersection. So there we go. I had to zoom out a little bit. And All right, so now we have both equations plugged in. Sorry, I'm having some technical difficulties here. I can't get my screen to look kind of how I want it here. There we go. That's what I'm looking for. All right, so can't see the lines as is, so we need to zoom out, and so we can see that point of intersection. Keep zooming. All right, so there we go. And we can see they cross at 27.5, comma 522.5. 27.5, comma 522.5. All right, so now to interpret the answer, what's the airspeed? Remember, Y stands for airspeed. All right, so we'll just answer it part by part. Airspeed. And remember, that means the speed of the plane if we were flying in a vacuum. If there was no wind affecting it, would be 522.5 miles per hour. And then the speed of the wind, which is what's affecting our actual speed, which in this problem they call the ground speed, is 27.5 miles per hour. All right, so looking at B, since I had, I'll probably just end the video there, but if you want to see any additional example from this video, I have one extra of each. You can see them written out on the paper, which I go into a little more in depth how to solve them algebraically. The big thing though is, can you define your variables? Can you write your system? And then can you interpret your answer? Okay, that's how we're going to kind of play this. As always, you'll have a Math Excel to go along with this, so look for section 6.4 Math Excel. Hope this helps. Thanks.